BCEF is cyclic and O lies on EF. So I guess we want to draw like the anti-parallel. But basically, we draw, I think we draw the tangent to A, and then we draw the parallel to that through O. I think that's how you do it, right? So like this. Let me try it. So E is on AC. And this is F. So that's going to be parallel to the tangent at A. I don't know if it's worth just drawing the tangent at A. We'll just draw a little mini tangent, so we know they're parallel. And we draw the intersection of EF with the arcs. Okay, so R and S. So this is S. This is R. And we reflect R about C and S about B. Interesting. So those are kind of far away, right? So I might want to shrink the diagram a little bit. Reflect R about C, S about B. So like this. Have that right? And okay. P and Q lie on BS. This is K. And this is L. P and Q lie on those two such that PK and QL are parallel to BC. Okay. PS, BS. So we drop perpendiculars to these two. Okay. So this is P and this is Q. Okay, so this isn't as bad of a diagram as I thought it might be. So we want to show the circle with center P and radius PK. It's tangent to the circumcircle RC. See, this is where it gets weird. So those circles would be tangent. That's very tricky. Yeah, that's a very weird problem. Okay. So if those are tangent, then we're supposed to have that circle with center Q and radius QL tangent to BFS, which would be a huge circle. That doesn't look true, but I don't know if my diagram is probably not perfect. Yeah, so it's probably just, yeah, my diagram is not perfect. And the better my diagram is, the more so it looks like it almost doesn't look true. Oh, BF. Yeah, that's weird. Wait. Okay, let me hide some stuff so it doesn't look so messy. So what are they saying? So this circle with center P and radius PK is tangent to RCE. See, it looks like right about here it's tangent, but then it looks like these are not yet tangent. Like, it almost seems like it's not true, right? But what if I? That's hard to tell. Yeah. So here, so this is RCE, and these are like very close to being tangent, right? RCE and this. Then if we have this circle, with BFS, there's like a gap. And if I try to make these look closer to being tangent, like here, it's like, it looks like they intersect at 2 points, right? And it looks like there's still a gap here. Yeah, like here, the circles intersect at 2 points, but there's still a gap here. So doesn't it almost look like it's not true? I don't know if I messed up in the diagram somehow. Right? Like if I zoom in, there's a gap here, but these intersect. Right? Let's see. Let me read the problem again. So possible I did something wrong. So E and F are on AC and AB. So O lies on EF and BCEF is cyclic. That seems true. R and S are the intersections of EF with arcs AB and AC. Okay. K and L are the reflection of R over C and S over B. Let's check that. I think that should be true. So that's true. And that's true. And then P and Q lie on BS and RC, such that PK and QL are perpendicular to BC. That's true. Yeah, it almost looks like the problem's not true, doesn't it? So yeah, but this one just looks so hard. Like, hey Ravi, thanks for joining. Ravi, did you take the IGO? Or did you participate in the Iranian Geometry Olympiad? Okay. Yeah, Hakan and Khan did it, so I didn't. This was the only problem they hadn't done already yet, so that's why I chose it. But yeah, it looks really hard. And this diagram makes it almost look like it's the problem's not true. So yeah, I'm not sure. Okay. P5 is so hard. So you want to try P4? Maybe we can come up with a different solution than or Khan found originally. So we could start working on it, and maybe we'll find something different. I don't know. All right, I'm gonna go to a different problem from it. So let's see, what's P4? Oh, P4 is also like an if and only if, or prove that if those are cyclic, then that's true. So, all right, let's try it. So we have a trapezoid. What was this? Did you do this one? So this was the last problem from the intermediate. Did you guys already do this one? Let's try this one. This one looks kind of interesting, actually. So we have ABCD is inscribed in a circle O, the center O. So and P is the intersection of the diagonals. And Q is a point on OP. And E and F are the projections of Q onto AD and BC. This is interesting. So it almost looks like AB is a diameter there, so I'm going to fix that. Okay, so we drop a perpendicular from Q to AD and BC. And that's E and F. And those points should already be E and F, so I don't have to change the name. All right. So maybe it looks like Ricard's theorem might be useful here, but we'll see. So then we draw the circle QEF. Yeah, so this is we're gonna want to probably intersect BC and AD because that's gonna lie on that circle. Okay. And then we could use Ricard's theorem. All right. So QM is parallel to AC. And QN is parallel to BD. So we have this and this. This looks interesting. This is M. And this is N. We want to show that ME and NF intersect on the perpendicular bisector of CB. It's a very random problem. Okay. So ME, maybe they're both. So whatever this point is, H, we want to show that CH equals HD. Yeah, a very weird statement, but okay. Interesting. We have two parallels. Two sets of parallels. Yeah, it's I haven't seen too many statements like this. Prove that two lines meet on the perpendicular bisector. So I wonder if there's some other cyclic quad here that we could find. Are G, Q, and H collinear? That would be nice, but yeah, it's not true. So O should lie on the perpendicular bisector of CB, right? So, I mean, it's the same as saying OH is perpendicular to CB, right? It's the same as saying, yeah. Yeah, it's such a weird statement. And I don't know how hard this problem is, because it's like the hardest problem, but of the intermediate. So it's not the hardest problem of the hard. It is the hardest of the intermediate. Okay. Where to go from here? Do we want to draw the midpoints BC and AD? That would give us some information.
What was that Picard term you were talking about?
Oh, what did you say?
What was that term that you were talking about? You said something like Picard's theorem.
Oh, Bricard. Yeah,
Oh,
I was
Brocard.
thinking,
Okay.
yeah. So, yeah, might be helpful to draw this point right here. So then we have OP is perpendicular to IG. So if OP we know is perpendicular to IG, and we want to show OH is perpendicular to CD, I wonder if, yeah, so is it equivalent to showing POH plus GID is 180? I think so. So GID is 96 and POH is 83 point, and yeah, if you add those up, it's 180. So if we could show those out to 180, that solves the problem. So maybe there's some cyclic quadrilateral here. I doubt these are actually tangent, but let's, yeah. So maybe it's worth drawing, because OP, so here's the McKell point, and it lies on this, right? I think, so yeah, that's a well-known fact. So yeah, these are all collinear right here. O, Q, P, J, and it's perpendicular to IG. And so basically, if we let OH, well, what we could do is we could take the midpoint of CD. I mean, if we take the midpoint of CD, then we have a cyclic quadrilateral, right? So we want to show that. So if I hide OH, I mean, we want to show that OK. It's the same issue as saying that OK, ME, and NF concur at a point. So yeah, maybe I could think about it that way. Like we want to show three lines concur, and we have a cyclic quadrilateral here. Yes. So yeah, how do I show three lines concur? I'm going to hide this for a sec until I find another use for it. So like what I could do is I could let whoops, what did I do there? I could let OK meet NF at a point H prime, and then like let it meet ME at H double prime and try to show they're the same point. Or it's probably easier to do it the other way. Like let NF meet OK at H prime and let ME meet OK at H double prime and show that those are the same point. So maybe I could use ratios or something. So like, say I did that. maybe I could show like OH prime equals OH double prime or something. Or, yeah, I don't know if I could use the SARGs or something. Might be hard. So, like, could I show that OEF and KMN are perspective? I don't have that much confidence in that idea. Although, yeah, is M the midpoint of the arc? No. I have to use the parallels somehow. I realize that. So H prime K times H prime O, that's like the power of H prime with respect to this circle. What is the center of this circle? Oops. It's going to be the midpoint of IO. Yeah, I want to show that H prime equals H double prime. That's kind of my idea here. Can I project through something? So let me see. So what were the parallels? So this, yeah. Trying to project through the right thing. I'll be right back. Thanks for waiting. That's a very weird kind of problem. And I use Menelaus somehow. So let's think about this. I want to find this ratio. And this is perpendicular. And this is also perpendicular. So wait. Oh. Let's see. This MFEN isosceles. Let's check. Could be true because of all those parallels. I wouldn't be surprised. It certainly looks true. Let's see. Yeah, it is. I don't think it's true that FP and E are collinear, though. Yeah, that's a coincidence. But yeah, it is an isosceles trapezoid. Yeah, okay, yeah, you can prove it easily by angle chase. Is F the midpoint of H prime N? I would be very surprised if that was true, but oh, it's very close, but no. Because yeah, let's do it. Yeah, so close. But let's yeah, I'm trying to make it like farthest. Yeah, because like something like this, it's clear that it's not. I wonder if there's just something special about this point other than is there any other? I doubt that's actually tangent. Let's see. NM, EF, and CD. Yeah. So basically, yeah, H lies on 3 different perpendicular bisectors. That's a good point. Yeah. So once we know that this is an isosceles trapezoid, yeah, maybe it's easier to draw it like this instead. First draw that point and then show that, yeah, OK and H prime are collinear. So Yeah, I'm trying to make this look a little farther away from point K, but it's hard to do that. I guess here, yeah, it's a little farther away in that case. So we have this isosceles triangle here. Let's see. E and F. So we have PJ times PQ is FP times FE. I'm not sure. Yeah. Maybe we can like reverse engineer this problem somehow. So like you have to use this parallel. So we know angle NQM is angle CPD. See, what time is it? 11:12. Okay, so we really haven't worked on this that long actually. Yeah, it's tricky. So maybe we could try to use the radical axis theorem somehow. Does okay. So like if we take the midpoint of AC, another way of saying this is we want to show H prime lies on the radical axis of these two circles, right? So we have this and this, and we want to show H prime lies on the radical axis. Okay. Trying to see if I can use Casey's theorem somehow. So I mean, the thing is, I mean, really there's three circles with that radical axis, right? So also this one. Let's see, this, and this. So their centers are collinear. We want to show H lies on the radical axis. Well, what do we know about them? Let's see. So this circle passes through J, E. Yeah, I can't think of a good way to use Casey's theorem. You guys want to try another problem or stick with this for a little bit? What do you think? All right, I think I'll try another problem. I feel like we've been stuck on that for a little while. Let's see, what is the number 4 intermediate? Oh, this one might be too easy. Number 2. The number 3. Let's see. M and N are on those two sides. So number 3 is kind of interesting. We could try that. Let's see. I think it might take some work to draw the diagram though, but let's try this. So yeah, Hakan and Khan, did you do the intermediate problems also, or mostly the advanced? Okay. All right, so these are new. That's good. Yeah, this one might be a little easier. Let's see. Yeah, I solved the first problem on the intermediate. It was really easy. Yeah, it was like trivial. So we have the circumcenter of ABC and arbitrary points on AC and BC. So I wonder if we have like arbitrary, maybe we want to make C at the top if it's like that. This is P3, I believe, of the intermediate. Let's see, P3 of the intermediate. Okay, so O is the circumcenter, and then we have arbitrary points on AC and BC. And an N. That's pretty arbitrary. They can just be any points they want. This is N, and this is M. And CMN is similar to PAN. Okay. So kind of like let me think how to do this. Like we want an angle here that's equal to, so yeah, I think we can draw the circumcircle CAN. And then P has to lie in that circle. Spiral similarity at N. So P is some point on this circle, and we want PAN to be similar to CMN. So we want this angle to equal this angle. And we want, okay, so we draw the isogonal to MN, and I think that would do it. So let's draw an isogonal. So we have the angle bisector. And we do some reflecting. Okay. And I think this is point P. see. That's P. Yeah, let's. Okay. So is it true that PAN is similar to CMN? I think it should be. Yeah. Okay. And then I'll do the same with Q, point Q. Let me see. Okay, so I drew the circumcircle CAN. Now I want to draw the circumcircle CMB. And draw an isogonal to NM. Just draw the circle centered at O. Okay. Yeah, that's a good point. It's this point. So then QMB. Is that right? Yes. CPAN and QCBM are both cyclic. Okay. All right. And this circle I will hide because we don't know it's true. We can hide this and this too, really. Well, we might not want to hide that because that's part of the similar triangles. Okay. So, I mean, that's the same as saying that P and Q have the same power with respect to this circle, right? And okay. Let's see. So we could try to use Casey's theorem a little bit. So the difference between the powers of P with respect to these two circles. Yeah, what's the center of the circle? That would be 2OD. So yeah, let's draw the centers of these two circles. So the way I have it, we want to show that OD over OE is the distance from Q to BC over the distance from P to AC. If we can show that, that would solve it. Although it doesn't look that easy. Um, let's think about this. So it's tricky. I like the idea of using the powers, but I'm not sure how to continue from there. Actually, maybe that's not so bad. So we want to show, basically, if we use Casey's theorem, we want to show that OD over OE is the ratio of the altitude from P to AC and the altitude from Q to BC. So let's draw those. Yeah, it's hard to make it look perfect, but I want to show that PF over QG is OE over OD, and that would solve it. We might have some similar triangles because we have so many equal angles. So are these triangles similar right here? I don't know. No. That would have made things easier. Yeah, I want to calculate PF over QG. So PF is PA. So CNP, so NP and NM are like, I think they're isogonal, right? Maybe I'm wrong. But these are equal. Yes. So PF is PA sine of PAC, which is PA sine of CNP, which is PA sine of MNA. Okay. So I think I'm getting something interesting here. So here's kind of what I'm thinking. In fact, maybe PF equals OE. I don't think it's true, but I think it's worth checking. That's PF and this is OE. Yeah, they're not equal. But here's what I'm thinking. Let me write this on a piece of paper first before I type it all up. Find a good pen. PF is PA sine PAC, which is PA sine PNC, which is PA sine MNA. So PF over QG is PA over QB times sine of PNC over sine MNA. And that is, so PA over QB, that's like PA over CM times CN over QB times CM over CN. So CM over CN and then sine A and MB. Okay. B and B. Okay. And okay, so this is MN over AB. CN over QB is now PA over CM is AN over MN times MN over BM, CM over CN, sine NMB. Okay. Yes. Okay. just these two circles? So not the circle of ABC, right? Okay. HA and IB. Okay. Let's see. Can I make it? All right. That'll be J. Almost looks isosceles, doesn't it? I don't know if that's actually true. Yeah. Are HMA and I and B, yeah. Well, actually, I'm not sure about that. Okay, so those aren't isosceles, but the whole thing is isosceles. Yeah, that's obvious. Binomial chase. Okay. PCQ are collinear. Oh, really? How did I miss that? PC and Q are collinear. It's really that easy, I guess. We just missed it. Okay. Okay. So yeah, that's really interesting that JHI is isosceles. So yeah, if you guys can figure out anything about OD and OE, I think there's a good chance that might help me solve the problem. Let's see. PCAH is an isosceles trapezoid. Interesting. So OP equals OH and OQ equals OI. And then does that solve it? Let's see. Is it obvious that, so we need to show OH equals OI, and we know JHI is isosceles. Interesting. So yeah, looks like we're very, very close. BOCJ is cyclic, and we're done. I don't think you mean BOCJ, right? AOCJ. No, you must mean so. AOBJ, I think you mean, right? Yeah, AOBJ. Okay. And then once we know that that's cyclic, so OA equals, so yeah, I guess it's kind of obvious that AOBJ is cyclic because O, like JO bisects, well, okay. Yeah, all right. So I'm going to delete these extra points I added. That seems like a much more elegant solution than what I had. All right. Okay. So let MN meet ANC and QMB at H and I. Okay, so I kind of just assumed that this was cyclic. So by an angle, so angle AP. APN is MCN. So PCNA is cyclic. Similarly, CQIB is cyclic. Okay, yeah, H and I. Okay, helps us use the similarity. So let HA meet IB at J. And then angle AHN is APN. Equal to angle MQB, which is MIB. So that means that JH equals JI. Okay. Next, we are going to show that this is cyclic. And once we know that's true, then, okay. So first I'm going to show this is an isosceles trapezoid. So angle, it's because these are orthogonal, right? So there's probably an easier way to say this, but angle CNE H is CNM, which is PNA. CNH, which is PNA. So PH is parallel to CA. And then similarly, QI is parallel to CB. Okay. And now we are going to show, OP, by symmetry, OP equals OH and OQ equals OI. And then now we want to show that this is cyclic. So let's think about this. Probably just by showing the angles add up to 180, right? Because angle AOB is twice angle ACB. And then, yeah, it's an angle chase. Equal to angle, so that would be twice angle AHN. And that is 180 minus AJB. And that means that AOBJ is cyclic. And AO equals OB implies that JO bisects AJB. JB. And that implies OH equals OI, implies OP equals OQ. Wow, very nice. So you got to do it purely synthetically. That's great. All right, we only have 9 minutes left, so let's see what we can do in 9 minutes. There was like I think there was like a pretty easy problem. So maybe this one we can solve. Now it's 8 minutes. Yeah, I think you can solve this one in 8 minutes. I think this is number 2, and I'm having some trouble maximizing. But there we go. So BA is tangent to the circumcircle of ABC. Okay, so then BA, if we draw the symmedian, then that's harmonic. That's usually the first thing I think of when I draw the tangent. So we have this point D, and E and F are the circumcenters of ABD and ACD. Interesting. This almost looks a little bit like Kel's theorem, maybe. E and F. M is the midpoint of EF. We want to show the line. Let's see what it says. The line tangent to that circumcircled AMD at D is also tangent to ABC. Okay. Oops. So I drew it fast. So it's saying the tangent at D here is also tangent to ABC. It's kind of interesting. So yeah, I think this is intermediate instead of advanced, but I'm not sure. Oh, is this the beginner round or is it intermediate? Let's see. Okay. That looks okay. Let's move the labels away. Let's see, he's still on. All right. Okay, so ABD and ACD, we have the line, the midpoint of the centers of those two. I wonder if AG is a symmedian. You guys think AG is a symmedian? Let's check. Yep, good guess. I get. So basically, we just a definition of. Oh yeah, that's right. Yeah, we want to show AG as a symmedian. But wait, but we know that that's tangent. Yeah, so that solves it, right? Because the tangent and the symmedian form a harmonic bundle with AB and AC, right? And so, yeah, ABGC is harmonic. And so the tangents at A and G and BC concur at a point. Oh, but we have to show that that passes through the midpoints. Okay, so it's not that easy. Okay, so yeah, that's a symmedian. So it's probably best to, let's see, ABD. Okay, so we define D like that. And we want to show that for AMD it's tangent. So we want to show angle. Yeah, let's think about that. Yeah, it's not that easy. I thought it was. Are AEF and ABC similar? That's interesting. Let's see. Oops. Yeah, it looks like they are. Good observation. So that means a spiral similarity takes one to the other. Yeah, okay, because AEB, we can show it's similar to AFC, right? That's probably just an angle chase. Yeah. So since AEB is similar to AFC, then they're similar. So M and H correspond, and M and H correspond in that similarity. We need to show that angle MDG is like MAG or something. And MDG is MAD. But MAD has like a similar. Oh, but MDG. Let's think about this. Is this isosceles? No. Yeah, I think we're really, really close, but we're out of time. So yeah, some interesting observations. But yeah, we can finish it off after the session. So thanks everyone for joining today, even though it was the World Cup. So yeah, I hope your favorite team wins. I don't think it's over yet, is it? Still, yeah, I don't know. I'll figure it out soon enough. So yeah, thanks everyone for participating. We had a lot of really nice solutions today. And for everyone watching on YouTube, thanks for watching. So if you want to join us in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video. And we meet every Sunday at 8 a.m. US Central Time. So thanks again and have a great day.